The morning of January 14, 1945, in the forests outside Houffalize Belgium, Oberleutnant Franz Hoffman crouched behind a snow-covered stone wall, watching American artillery shells streak overhead toward German positions 300 yards distant. After 31 months of combat across 3 fronts, Hoffman understood artillery with the intimacy of a man who'd survived it. He knew the sound of different calibers, could estimate distance by the whistle pitch, and had developed instincts about where to find cover when the barrage began. But something was wrong with the American fire this morning. The shells were detonating at precisely the wrong altitude, or rather, from the German perspective, at precisely the right altitude to kill everyone. 23 meters above the ground, Hoffman estimated, watching fragments spray downward in a perfect cone. Not 30 meters like the random variance of time delay fuses. Not ground level like impact detonations. Exactly. 23 meters, shell after shell, with mechanical precision that defied every principle of artillery science he'd learned at the Jüterbog Artillery School in 1940. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Wehrmacht had concluded years earlier that consistent airburst artillery was technically impossible. The mathematics were straightforward enough. A timed fuse could theoretically detonate a shell at a predetermined altitude, but the variables made precision unattainable. Powder temperature affected burn rate. Barrel wear changed muzzle velocity. Atmospheric pressure and air density varied with weather. A fuse set to detonate at 70 feet might explode anywhere between 50 and 500 feet, depending on conditions, making the entire concept operationally worthless. Yet the Americans were doing it. Hoffman watched another salvo impact, each explosion blooming at identical heights above the frozen earth. The fragments descended through the canopy of bare winter trees, turning every foxhole into a trap. 3 men from his platoon were already dead, killed by steel that came from directly overhead. Traditional cover meant nothing against weapons that attacked from the sky. That afternoon, examining an intact fuse recovered from a dud shell, Hoffman made a discovery that fundamentally altered his understanding of American industrial capability. The fuse contained what appeared to be a miniature radio transmitter, complete with 4 glass vacuum tubes, each smaller than his thumb. These delicate components had somehow survived being fired from a cannon at accelerations that should have pulverized them into powder. The fuse weighed approximately 1 kilogram, and measured perhaps 8 inches in length. Inside that cramped space, American engineers had packed a complete radio system capable of detecting reflected signals and calculating detonation timing with precision measured in microseconds. The story of how American scientists achieved this seemingly impossible feat began not in the frozen forests of Belgium, but in a converted automobile garage in Silver Spring, Maryland, where, in the spring of 1942, a team of physicists were wrestling with a problem that every major military power had examined and rejected as unsolvable. The challenge was deceptively simple to state. Create a fuse that would detonate an artillery shell at a precise distance from the target, not at a predetermined time or upon impact, but when the shell actually approached within lethal range. The National Defense Research Committee, established in June 1940 under the direction of Vannevar Bush, had assembled leading American scientists to address critical military problems. Among them was Merle Tuve, a physicist at the Carnegie Institution, whose Section T would eventually employ over 1,000 researchers, working on proximity fuse development. The technical obstacles they faced would have discouraged less determined engineers. Consider what was required. The fuse had to fit inside the nose of a 5-inch naval artillery shell, leaving space for 7 pounds of high explosive. Within that confined volume, engineers needed to install a complete radio transmitter operating at approximately 200 MHz, a receiver sensitive enough to detect reflected signals from aircraft or ground targets, a power source that could function reliably after months of storage, safety mechanisms to prevent premature detonation, and a triggering circuit that could process signal data and fire the detonator within milliseconds. All of this had to survive the violence of being fired from a gun. When a 5-inch shell launches, it accelerates from 0 to 800 meters per second in roughly 6 meters of gun barrel. This creates forces exceeding 20,000 times Earth's gravity. Every component experiences stress equivalent to being struck by a sledgehammer while simultaneously spinning at 25,000 revolutions per minute as the shell engages the rifled barrel. After surviving this mechanical trauma, the electronics had to function perfectly during perhaps 20 seconds of flight time. The German military had explored proximity fuses extensively. As early as 1930, engineers at Rheinmetall-Borsig developed over 30 different prototype designs, including acoustic sensors that would trigger on engine noise, photoelectric cells that would respond to light from target aircraft, and electrostatic detectors that would sense the electrical charge surrounding metal structures. By 1939, Wehrmacht technical intelligence had concluded that while the concept was theoretically valid, the engineering challenges were insurmountable with available technology. The official directive from Hitler's High Command in 1940 prioritized only weapons that could reach production within 6 months to support the planned invasion of the Soviet Union. Germany's proximity fuse programs were cancelled, though limited research would resume in 1944 when the war situation became desperate. British researchers had advanced further. Scientists at the Telecommunications Research Establishment conceived of using miniature Doppler radar systems. They built working prototypes and tested them on rockets, which faced less severe acceleration forces than gun-fired projectiles. But Britain's program encountered 2 critical barriers. The manufacturing cost was astronomical at a time when Britain's industrial capacity was already stretched beyond limits. More fundamentally, British engineers could not solve the miniaturization problem. The smallest vacuum tubes available, those designed for hearing aids, were still too fragile to survive artillery acceleration forces. By 1941, British prototypes achieved perhaps 50% reliability under ideal conditions. For military deployment, this was unacceptable. The British shared their research through the Tizard mission when America entered the war. American scientists studied the British work and concluded that success required not just better engineering but fundamentally different manufacturing approaches. The Applied Physics Laboratory, established at Johns Hopkins University specifically to develop the proximity fuse, settled on a radio-based system using Doppler radar principles. The physics were elegant in theory. A miniature transmitter in the shell's nose would emit radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the Doppler effect would shift the frequency. When the frequency shift indicated the target was within lethal range, an electronic circuit would close and detonate the warhead. Making this work in practice required solving problems that seemed to violate physical laws. The key challenge was the vacuum tubes. These delicate glass components contained thin filaments that glowed when heated by electrical current, emitting electrons that flowed through a partial vacuum to create amplification and switching circuits. Conventional vacuum tubes were designed for radios and amplifiers that sat safely on tables or in cabinets. Subjecting them to 20,000 times Earth's gravity would shatter the glass envelopes and snap the filaments like thread. James Van Allen, a young physicist who joined the Applied Physics Laboratory as a founding member in April 1942, took responsibility for developing what the team called ruggedized vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had created for hearing aid applications. These were already smaller and more robust than standard radio tubes, but they were designed to survive being carried in someone's pocket, not fired from a cannon. Working with engineers at Sylvania Electric Products, Van Allen redesigned the tubes from fundamental principles. The glass envelopes were thickened significantly and carefully annealed to remove internal stresses that could cause shattering under shock. The internal filaments and grids were redesigned with shorter unsupported spans and heavier wire gauges. Every structural element was analyzed for failure modes under extreme acceleration. The tubes were potted in wax compound inside the fuse body, which cushioned them against shock loads while also damping vibration. Testing required destructive experimentation on a massive scale. The team used a vertical test gun at the Dahlgren Naval Proving Ground in Virginia. Complete fuses were fired straight down into soft earth, which caught them gently enough that researchers could recover intact specimens and examine them under microscopes to identify failure points. Through hundreds of test firings and thousands of design iterations, the Privex team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement over conventional anti-aircraft fire, authorized mass production tooling even with this marginal reliability. Engineers were confident they could improve performance during production ramp-up, and subsequent development proved them correct. By early 1943, reliability exceeded 90%, but vacuum tubes represented only one challenge among many. The fuse required a power source capable of delivering electrical current immediately upon firing and maintaining output for up to 40 seconds of flight time. Conventional batteries were too large and suffered from limited shelf life, particularly in tropical heat. Engineers developed a reserve battery design using liquid electrolyte kept separate from the battery plates by a membrane. When the shell fired, centrifugal force spun the electrolyte outward through the membrane into contact with the plates, generating electricity instantly. This gave the batteries indefinite storage life while ensuring immediate activation. Safety mechanisms required extraordinary attention. The fuse could not arm until the shell had traveled well clear of the launching ship or gun position. It needed protection against accidental detonation from radio interference, including signals from friendly radar systems. It required wave suppression circuitry to prevent premature triggering when fired at low angles over water, where the ocean surface could reflect radio signals. Each safety feature added complexity and components to an already crowded package. The most critical specification was detonation distance. The entire purpose of the proximity fuse was to explode the warhead at the optimal range from the target. Too far, and the fragments would spread too widely, reducing hit probability. Too close, and there might be no time for the detonation sequence to complete before the shell passed the target. After extensive analysis of fragmentation patterns and target vulnerability, engineers determined the ideal detonation distance was 20 to 25 meters for anti-aircraft use and 20 to 30 meters for anti-personnel ground bursts. Achieving this precision required solving a complex problem in radio frequency engineering. The fuse's transmitter emitted continuous wave radio signals. When these waves struck a target and reflected back to the shell, the Doppler effect shifted the frequency. A target approaching the shell would cause the reflected frequency to increase. A target moving away would cause it to decrease. The magnitude of the frequency shift depended on the relative velocity and the distance. The receiving circuit had to detect this shifted signal, filter out noise and interference, and determine when the frequency shift indicated the target was within the predetermined range. The calculation had to happen in microseconds as the shell hurtled through space at 800 meters per second. At that velocity, the shell covered 23 meters in roughly 29 milliseconds. The detection, processing, and detonation sequence had to complete within that window. Engineers designed the circuit to trigger when the reflected signal reached a specific frequency offset from the transmitted frequency. This offset corresponded to a precise distance. For naval anti-aircraft fuses, the trigger point was calibrated for approximately 23 meters. For ground artillery fuses used against personnel, the setting was adjusted to detonate at heights between 20 and 30 meters above the surface. The Mark 32 fuse for the Navy's 5-inch gun, designated VT fuse in official documents with the deliberately misleading expansion variable time fuse to conceal its true nature, measured 8 inches in length and weighed just over 2 pounds. Inside its steel casing were approximately 130 miniaturized electronic components, including 4 vacuum tubes, dozens of resistors and capacitors, the reserve battery, safety switches, and the detonator assembly. The entire unit cost $732. When production began in 1942, an astronomical sum equivalent to roughly $12,000 today. But American industrial capacity was just beginning to demonstrate what mass production could achieve. 5 companies received contracts to manufacture proximity fuses: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly, with only 500 fuses per day by the end of 1942. By late 1943, output had reached 40,000 fuses daily. Over the course of the war, American factories produced more than 22 million proximity fuses at a total cost exceeding $1 billion 1940s dollars. The Crosley Corporation facility, Cincinnati alone, produced 5,259,113 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days per week, achieving peak output of 16,500 fuses daily. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. They signed security oaths and underwent searches when entering and leaving facilities. Most had no idea what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device's very existence was classified. Even its use in combat was initially restricted to situations where there was no possibility of a dud shell falling into enemy hands. The first operational test came on August 12, 1942, when the light cruiser USS Cleveland fired proximity-fused shells at radio-controlled drone aircraft in Chesapeake Bay. Using conventional ammunition, destroying maneuvering aerial targets typically required dozens of shells. Cleveland's gunners destroyed 3 drones with just 4 bursts, demonstrating effectiveness that exceeded every prediction. The first combat use occurred on January 5, 1943 off Guadalcanal in the Solomon Islands. 4 Japanese dive bombers attacked a U.S. Navy task force. As the aircraft broke off their attack run, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells. All 3 detonated near one aircraft at precisely calibrated range, shredding it with fragments. The aircraft plunged into the sea. Helena's gunners had achieved in seconds what would have required dozens of conventional shells and extraordinary luck. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to forward bases. Combat results exceeded predictions. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft destroyed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The improved hit probability meant that ships which previously required sustained fire to defend themselves could now knock down attacking aircraft with brief, accurate bursts. The true effectiveness was demonstrated during Operation Iceberg, the invasion of Okinawa in spring 1945. On May 11, 1945, 2 destroyers, USS Hadley and USS Evans, came under assault from approximately 150 Japanese aircraft during Operation Kikusui No. 6. Many were loaded with explosives for kamikaze suicide attacks. During approximately 85 minutes of intense combat, the 2 destroyers and supporting craft faced overwhelming odds. Hadley's gunners knocked down 23 enemy planes using proximity-fused ammunition before being hit by 1 bomb, 3 kamikaze aircraft, and 1 rocket bomb. Evans accounted for additional aircraft before being struck 4 times by suicide planes. Both ships survived despite catastrophic damage. The action report stated that proximity-fused ammunition was indispensable in preventing complete destruction of the formation, but for most of the war, the Pentagon strictly forbade using the fuse over land. The risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. Intelligence analysts estimated that if Germany equipped its anti-aircraft guns with proximity fuses, Allied bomber losses could increase by 300%, potentially making the strategic air campaign impossible to sustain. This absolute security restriction began to erode in June 1944, when Germany unleashed the V-1 flying bomb against London. This absolute security restriction began to erode in June 1944, when Germany unleashed the V-1 flying bomb against London. Launched from sites across the English Channel, The Vone second approached at speeds exceeding 600 kilometers per hour, faster than many Allied fighters could intercept. Small, fast, and arriving without warning, they were extraordinarily difficult to destroy. From June through late August 1944, Germany launched over 9,000 Vone second against Britain, inflicting tens of thousands of civilian casualties. British defences initially could destroy only 17% of the Vone second that entered the coastal gun belt. The situation was desperate. Prime Minister Winston Churchill authorised use of proximity fuses in anti-aircraft guns defending Britain, accepting the security risk as preferable to continued civilian deaths. Modified fuses were rushed into production, specifically calibrated for the small, fast V-1 targets. British and American anti-aircraft batteries along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar fire control systems. The effect was dramatic. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August 1944, 82% of incoming Vone second were shot down before reaching their targets. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining against the robot bombs. The V-1 campaign demonstrated beyond doubt that the proximity fuse was war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land where dud shells could potentially be recovered by German intelligence. The calculation changed completely in December 1944. On the morning of December 16th, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split the Allied armies and capture the vital port of Antwerp. The offensive took the Allies by complete surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. The weather was terrible with heavy snow and thick clouds that grounded Allied air power. German commanders felt confident that poor visibility would limit the effectiveness of American artillery, which relied on aerial observation for accurate fire. They were catastrophically wrong. On December 16th, the same day the offensive began, Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received a new type of ammunition, proximity-fused shells codenamed POSIT. But supreme, Commander Dwight Eisenhower had not yet authorized their use over land. The secrecy restrictions were still technically in place. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 30 meters above the ground, precisely calibrated for maximum lethality against personnel. The fragments spread in a cone-shaped pattern, covering an area far larger than ground bursts. Foxholes provided no protection. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. Traditional artillery doctrine held that soldiers in properly constructed foxholes had reasonable survival odds during bombardment. Ground bursts created predictable fragmentation patterns that travelled mostly horizontally. Experienced troops knew how to orient their positions to maximize protection, but proximity-fused airbursts changed every assumption. The fragments came from directly overhead in a spreading cone that filled foxholes and trenches with deadly steel. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department describing an action near the Sauer River. His Third Army had caught a German battalion attempting to cross the river in darkness. American artillery saturated the area with proximity-fused shells set to detonate at precisely 23 meters altitude. By actual count conducted the following morning, 702 enemy soldiers were killed in approximately 12 minutes of firing. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies possessed this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction that he was glad American scientists had thought of it first. The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Colonel Otto Skorzény's Panzer Brigade 150, part of an elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effect. The airbursts so unnerved the attackers that some German soldiers charged directly into American defensive positions seeking any shelter from the overhead explosions. The attack was repelled by afternoon with catastrophic German casualties. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German prisoners of war interviewed by American intelligence officers captured the psychological impact with stark clarity. One German artillery officer captured in January 1945 described the proximity fuse as demonstrating a fundamental difference in industrial capacity between Germany and America. American engineering, he said, solved impossible problems through massive application of resources and acceptance of high costs. The proximity fuse required extraordinary manufacturing capacity and willingness to invest billions in a single weapon system. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure while simultaneously producing tanks, aircraft, ammunition, and all other necessities of modern warfare. Another prisoner, a Luftwaffe engineer who had worked on German proximity fuse research before the program was cancelled, focused on the technical implications. If Germany had possessed proximity fuses for anti-aircraft use, he estimated the Allied strategic bombing campaign would have become unsustainable. Loss rates of 15 to 20% per mission would have forced cancellation of daylight bombing operations, but he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapons program and mobilize over 100 factories for production. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate and visceral revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match, and deployed with a precision that made traditional defensive tactics obsolete. The Battle of the Bulge demonstrated how American artillery doctrine had evolved to maximize the fuse's effectiveness. Forward observers called down fire not just on visible targets but on suspected positions and likely assembly areas. Artillery batteries laid down barrage patterns covering entire grid squares. The proximity fuses meant that every shell was an effective airburst. There were no duds that buried themselves harmlessly in mud, no premature ground detonations that wasted explosive power against earth rather than personnel. German tactical doctrine developed over 6 years of warfare had to be completely rewritten. Traditional defensive positions with overhead cover designed to protect against ground bursts suddenly became death traps as fragments penetrated from above. Moving in the open during artillery fire, always dangerous, became suicide. The Germans tried to adapt by dispersing more widely and staying constantly mobile during American fire missions. But adaptation had limits. The proximity fuse fundamentally altered the tactical equation in ways that no amount of training or experience could overcome. American intelligence reports noted that German commanders were offering substantial rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. By January 1945, Wright Field in Ohio had developed electronic countermeasure systems designed to jam the fuse's radio signals based on the assumption that captured German fuses would lead to German jamming efforts. But German engineers never fully recognized what they had captured. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, German technical intelligence analysts examining captured fuses initially failed to grasp that miniature radio transmitters were inside every shell. Some reports described them as advanced impact fuses, with unusual mechanical components. The concept that American industry could manufacture millions of miniature radios capable of surviving 20,000 times Earth's gravity simply did not fit within German understanding of what was technically achievable. The detonation precision that so devastated German forces resulted from extraordinarily sophisticated radio frequency engineering. The fuse operated by continuously transmitting radio waves at approximately 200 MHz. When these waves struck a target, whether aircraft, ground vehicle, or even terrain features, they reflected back to the shell. The Doppler effect shifted the frequency of reflected waves based on the relative velocity between shell and target. The receiving circuit was tuned to trigger when it detected a specific frequency offset corresponding to a range of approximately 23 meters. At this distance, the expanding fragment pattern from a 5-inch high explosive shell created optimal probability of hitting targets while minimizing wasted energy. The fragments from a shell detonating at 23 meters altitude spread in a cone approximately 50 meters in diameter at ground level, creating a lethal zone far larger than ground bursts could achieve. The precision was extraordinary. German time delay fuses for airburst fire typically had variance of plus or minus 150 meters in detonation altitude, depending on powder temperature, atmospheric conditions, and manufacturing tolerances. This made them operationally unreliable, except in massed fire, where statistical probability ensured some shells would detonate at useful altitudes. American proximity fuses detonated within plus or minus 3 meters of the target altitude, regardless of external conditions. This 9-meter variance window represented a 50-fold improvement in precision compared to time delay fuses. The mathematical elegance of the Doppler detection system was matched by brutal pragmatism in circuit design. Engineers deliberately kept the system simple to maximize reliability. The fuse used only 4 vacuum tubes where more sophisticated designs might have used 8 or 10. Each component was oversized with substantial safety margins. The triggering threshold was set conservatively to avoid premature detonation from spurious signals or ground reflections. This meant the fuse would not trigger at maximum possible range, but would reliably trigger within the optimal lethal radius. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. German fighter pilots attempting to intercept Allied bomber formations found themselves running gauntlets of proximity-fused fire from escorting ships and ground installations that made attack approaches suicidal. Ground combat intensified as American forces crossed the Rhine in March 1945. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with fragments, making defensive positions in buildings untenable. German troops attempting to defend Cologne, Mannheim, and other Rhine cities discovered that traditional urban defensive tactics became death sentences when American artillery could deliver precision airbursts that turned stone buildings into fragment generators. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe might have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defences equipped with proximity fuses might have made the D-Day landings unsustainable by shooting down transport aircraft and gliders carrying airborne troops. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance at the beaches. Technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch that would close, detecting specific engine frequencies. Rheinmetall Borsig developed an electrostatic fuse using capacitive detection of the electrical charge surrounding metal aircraft structures. There were optical fuses using photoelectric cells, magnetic fuses using coil detectors, and experimental radio fuses similar in concept to the American design. But none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired with reasonable success rates. By then, it was far too late. Germany lacked the industrial capacity to establish mass production facilities. Even if production could have been started, the resources required would have competed directly with production of tanks, aircraft, synthetic fuel, and basic ammunition. The German war economy by 1944 was operating at maximum capacity with critical shortages in every category. Adding a new complex weapons system, requiring dedicated factories, trained workers, and scarce materials was simply impossible. The American proximity fuse program succeeded because it possessed resources that dwarfed the entire German military research budget. The program consumed over $1 billion 1940s dollars, equivalent to roughly $16 billion today. This included not just research and development, but building dedicated production facilities, training tens of thousands of specialized workers, establishing quality control systems, and maintaining absolute secrecy around the entire effort. The production statistics were staggering. At peak output, American factories were producing 70,000 fuses per day. Each fuse contained approximately 130 individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters worldwide. This represented nearly 9 million components manufactured daily, every one required to function reliably after surviving artillery, launch forces that would destroy conventional electronics. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This represented a cost reduction of 97.5%, resulting from manufacturing innovations, improved efficiency, and economies of scale. At $18 per fuse, the weapon remained expensive compared to conventional fuses, costing perhaps $2, but the improved lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness was obvious value. The secrecy remained so complete that production workers at different factories did not know other facilities were building identical components. Suppliers manufactured parts without understanding their purpose or how they would be assembled. The security classification remained in force until September 1945, when the war ended, and the proximity fuse was finally revealed to the public through carefully managed press releases that emphasized American technological superiority. For German prisoners of war held in Britain who witnessed the defense against V-1 flying bombs, the revelation of what they had faced was profound. They could see anti-aircraft guns firing, and Vone's second exploding in mid-air with mechanical regularity. They understood that the same technology devastating their former comrades in the Ardennes was now protecting British cities with ruthless efficiency. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production. It was realization that they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding with brutal clarity. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war. Not because of the fuse itself, but because of what it represented. The Fuze was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match even at the height of its power. If America could build miniature radios that fit inside artillery shells, survived forces that would destroy normal electronics, and worked with precision measured in meters after being subjected to conditions that seemed impossible, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century, with 19th century assumptions about what was industrially and technically possible. The proximity fuse shattered those assumptions with every precisely detonated shell. The technological advances embedded in the proximity fuse were revolutionary across multiple domains. Miniaturized vacuum tubes required breakthroughs in materials science, particularly in glass composition and annealing techniques that prevented stress fractures. The printed circuit boards were among the first mass-produced examples of technology that would revolutionize electronics manufacturing. The reserve battery design using centrifugal activation was elegant and innovative. The radio circuitry was efficient and reliable. But perhaps the most significant advance was in manufacturing and quality control systems. Producing millions of complex electronic devices with consistent quality required processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that would become foundations of modern manufacturing. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes, following procedures that demanded precision and attention to detail. James Van Allen, the physicist who helped develop ruggedized vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite launched in 1958 and credited with discovering the Van Allen radiation belts used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The technology transfer went far beyond space exploration. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production of sophisticated devices. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions. Modern weapon systems use descendants of the World War II proximity fuse, the Standard Missile family, Patriot surface-to-air missiles, and virtually all modern air defense systems use proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing algorithms. They can discriminate between real targets and decoys, operate in intense jamming environments, and calculate optimal detonation points based on multiple parameters, including target size, velocity, and range. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation distance, and trigger the warhead for maximum effect. The 70-foot detonation distance that seemed impossible in 1940 became routine by 1943 and remains the foundation of modern air defense systems. The broader lesson extended beyond the proximity fuse to the entire character of American military production during World War II. America outproduced the Axis powers not just in quantity, but in quality and technological sophistication. American weapons were not always individually superior to German or Japanese equivalents, but American weapons worked reliably, were produced in overwhelming numbers, and included technological innovations like proximity fuses that provided critical advantages impossible for enemies to counter. The combination of quantity and quality was what made American production decisive. The proximity fuse provided a force multiplier that turned numerical superiority into overwhelming dominance. By the final year of the war, German forces were facing enemies who possessed better weapons, more weapons, and technological advantages that made traditional tactics obsolete. The casualty statistics reflected the impact. During the Battle of the Bulge, despite initial surprise and favorable terrain, German forces suffered disproportionate casualties. American artillery was responsible for an unusually high percentage of German losses. Medical personnel reported that wounds from proximity-fused shells tended to be more severe than wounds from traditional artillery. The fragments came from above, targeting the head and shoulders, where body armor provided no protection. Multiple fragment wounds were common. The lethality was significantly higher than ground bursts, which tended to produce lower extremity wounds with better survival rates. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany, proximity-fused ammunition had become standard for all American artillery battalions. Factories were producing fuses faster than they could be shipped to Europe. Ammunition. Dumps held millions of rounds. American gunners could fire proximity-fused shells without conservation, using them for harassment fire, interdiction missions, and speculative fire on suspected positions. The abundance was as devastating psychologically as it was physically. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and modulation characteristics. Without intact working fuses to analyze, German engineers could not determine specifications needed for jamming systems. Even if they had developed jammers, deploying them across every potential target area would have been logistically impossible, given Germany's collapsing infrastructure and critical shortages of electronic components. Physical countermeasures were equally ineffective. The fuses operated by detecting reflected radio waves. Reducing the radar cross-section of troops and equipment was impossible. The human body itself reflected enough radio energy to trigger the fuse at close range. Vehicles and weapons were even better reflectors. The only defense was dispersion, spreading forces widely enough that a single shell explosion would not catch multiple targets. But dispersion reduced combat effectiveness and made coordinated operations difficult. German tactical doctrine had evolved around concentrated formations that maximized firepower and command control. Dispersing to counter proximity fuses weakened overall capability, even as it reduced casualties per shell impact. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight when American observation aircraft could direct fire. They avoided any position that appeared to be a likely target. They dispersed to the point where unit cohesion broke down. Morale plummeted. The sense of helplessness broke the will to resist more effectively than any propaganda. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted as part of warfare, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda or intimidation, but through demonstrated futility of resistance. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.